So when doing electron configurations, we have to look at not only elements, as in the last session, but also with ions. And so with ions, there are three main groups, or actually four main groups of ions that we have. We have the S-block cations, and these we remove from the last s orbital. And typically S-block cations have the same electron configuration as the previous, or not typically, always, as the same electron configuration as the previous noble gas. And so S-block cations always have a filled, completely filled orbitals. And then we have next, we have the P-block cations. And here we remove from the highest, remove electrons from the highest p orbital. And then the highest s orbital. So you'll never remove electrons from a d orbital for a p block cation. It's always going to be the highest p and then the highest s. And then we have p block anions. And we add electrons to the highest p orbital. So most of these are straightforward. What gets confusing is sometimes with the d block cations. And so with the d block cations, we remove from the highest s orbital and then the highest d orbital. And you may say, well, when we fill these electrons, we fill the s orbital first and then the d. But why is it when we remove electrons, we remove from the s and then the d? And the reason is because once you add electrons into orbitals, into the s and d orbital, they switch in energy. So what happens is when you put electrons in, the s becomes higher than the d. So 4s is higher than 3d. But before you add them, when they're empty, 4s is lower than 3d. So that's why for transition metal cations, we take from the highest s and then the d, because when they have electrons, it switches. And so here with cobalt 3+, I'm going to write the electron configuration of cobalt. Which is 4s2, 3d7. And so with cobalt 3+, we're going to remove 2 electrons from the s orbital and 1 electron from the d orbital. So we're going to have cobalt 3+, argon 3d6. And since it's 3d6, if we remember, the d orbital has 5 degenerate orbitals. So since it's 3d6, everyone gets 1. Before it gets paired up. And therefore, cobalt 3+ has 4 lone electrons. Now with vanadium 2+, first write the electron configuration of vanadium. So this is the electron configuration for vanadium. Now the reason I chose vanadium is to make sure that everyone understands where to remove electrons first. So if you remove the 2 electrons from the d orbital first, you would have gotten 1 lone electron, which would have been incorrect. But here again, we remove from the s orbital first. So we remove the 2 electrons from the s orbital. So we have 3d3 left. And since 3 electrons in the d orbital is less than 5, you know that all 3 of these are going to be lone electrons. So this has 3 lone electrons. Next we have copper 2 plus. Now the reason that copper 2 plus was chosen because we have to remember our exceptions on the electron configuration. So copper, remember, is an exception to the off-ball principle, so it's going to be argon 4s1 3d10. And so here, if we were to write the electron configuration of copper 2 plus, it would be argon 3d9. So notice that if you would have wrote the electron configuration of copper incorrectly, let's say you put 4s2, never mind, it would have worked out. So here we have 3d9, so that means we're going to have 9 d electrons. So this is 6, 7, 8, 9. And so it has 1 lone electron. And lone electrons are important because that's how it determines if something is, as we'll see in a little bit, paramagnetic or diamagnetic. So here we want to identify the following species as paramagnetic or diamagnetic. And so just a kind of quick summary, paramagnetic is a species with lone electrons. So what that means, if you have lone electrons, it's attracted to a magnetic field. And so when you're looking for whether something is paramagnetic, look to see if it has lone electrons. And if it's diamagnetic, it has no lone electrons. So they're all paired. And that's the main difference between diamagnetic and paramagnetic. Paramagnetic, we're looking for lone electrons. Diamagnetic, they're all paired up. Now, before we look at the different species here to identify them, what we want to do is for elements, now this is elements, not ions, but for elements, there are certain groups on the periodic table that are always diamagnetic. And so those groups are group 2. So all elements in group 2 are always diamagnetic because they're always going to have a field s orbital. Likewise, the group with zinc, cadmium, mercury, this group here will always be diamagnetic elements. So they're always going to have a field, completely filled s and d orbital. And then the last group is group 18, the noble gases. Noble gases are always diamagnetic. Now for your main group cations, and main group cations, we're referring to group 1, group 2, those are your main group cations. Again, now we're talking about cations and your group 13 cations. These are going to be diamagnetic because if you remember, for cations, we're going to remove from the s and p orbital. So the main group cations of group 1, group 2, group 13 are not going to have any lone electrons. So those cations from those 3 groups would be diamagnetic. Now, likewise, your main group anions, so like here, if we look, these that are usually form anions, these are also going to be, the anions of these are also going to be diamagnetic. And so that can kind of help you narrow down, whether I have to really investigate or not. So mainly for the transition metal cations and some of your post-transition metal cations like tin and lead, even those would be diamagnetic. But so again, mainly the transition metal cations you have to investigate. So that's kind of a summary. So again, your group 1, group 2, group 13 cations are diamagnetic. Even 10 and lead cations are diamagnetic. So 10 2 plus, 10 4 plus, those are diamagnetic. And your main group anions are also diamagnetic. So lots of things are diamagnetic. The only things that are paramagnetic mainly are the transition metals, cations, as ions. As elements, we went over those groups. So again, the ones I highlighted in purple are the ions that are diamagnetic. So now we look here, we look at gallium 3 plus. Gallium 3 plus is a main group 13 elements or ion. So gallium 3 plus would be diamagnetic. Now chromium 4 plus, we'll need to write the electron configuration of chromium. It'll be argon 4s1 3d5. And so when we write chromium 4 plus, it'll be argon 3d2. And so since you only have 2d electrons, you know for sure that those are going to be lone electrons. So this would be paramagnetic. Next we go to barium. Barium is a group 2 element. Remember, group 2 elements, zinc, cadmium, mercury group, and the noble gases are elements that are always diamagnetic. Bismuth. Well, bismuth is not one of those 3 groups that we mentioned about elements that are diamagnetic. So bismuth is going to be paramagnetic. Now cadmium 2 plus, if we write the electron configuration of cadmium, it's going to be krypton 4s2, or excuse me, not 4s2, 5s2 4d10. And so if we make cadmium 2 plus be krypton 4d10. So it's going to have a completely filled d orbital. So this would be diamagnetic. And then lastly, we have hafnium 2 plus. So let's write the electron configuration of hafnium. It would be, what is it, xenon 6s2 4f14 5d2. So here with hafnium 2 plus, we're going to remove from the s orbital first. So we get hafnium 2 plus, xenon 4f14 5d2. So since you have 2 lone electron or 2 electrons in the d orbital, those are going to be lone electrons. So this would be paramagnetic. So again, just to recap, the elements that are circled in red, green are the elements that are always diamagnetic. The sections that I highlighted in purple are the ions that are always diamagnetic as well. So now we're moving to atomic radii. It's one of the periodic trends. And again, periodic trends means that it changes as you go across the periodic table. Now the trend for atomic radii, and we'll explain a little bit more in depth of why it occurs, but as you go from left to right, the atomic radius decreases, and as you go from top to bottom, the atomic radius increases. Now the reason that it decreases from left to right is something called effective nuclear charge. An effective nuclear charge is the actual charge felt by the electrons from the nucleus. Because the nucleus is positive charge, the electrons are negative, so they feel that attraction from the nucleus. Now, they don't feel the full attraction, as we'll see in a little bit. They feel some of that attraction, and that's where the effective nuclear charge comes from. And as you go from left to right on the periodic table, the effective nuclear charge goes up, the atomic radius decreases, because the greater the effective nuclear charge on the outer electrons, the more tightly held to the nucleus they are, so the smaller the radii. So again, as we go from left to right, atomic radii decreases, effective nuclear charge increases. Therefore, the reason that the atomic radii decreases is because the electrons are more tightly bound to the nucleus, causing them to shrink. So that's why you shrink as you go from left to right. Now, the opposite thing of effective nuclear charge is shielding. And shielding is the result of electron-electron repulsion. So what happens is the electrons, for example, we use the analogy or the outer versus the inner electrons. The outer electrons are shielded from the nucleus by the inner electrons, because the inner electrons have this electron-electron repulsion with the outer electrons. And so as you have more shielding, the outer electron has less attraction to the nucleus, so it's pushed further out from the nucleus, causing the atomic radius to increase. And so that's what happens when you go from top to bottom down a group. Down the group, you're adding more inner electrons. Therefore, you're adding more electron-electron repulsion, and it pushes those outer electrons further from the nucleus, causing the radius to increase. So again, as we go from left to right across a period, effective nuclear charge increases, atomic radius decreases. As we go from top to bottom, we add more inner electrons, shielding goes up, atomic radius increases. And to show you the difference in effective nuclear charge, just an example here, we have lithium and fluorine. Both lithium and fluorine have 2 inner electrons. Because remember, lithium is helium, or I should say 1s2, 2s2, 2p1. And fluorine, 1s2, 2s2, 2p7. So you see here, lithium and fluorine both have 2 inner electrons, whereas lithium has 3 outer electrons, fluorine has 9 outer, or excuse me, not 9, that's it, that should be a 5. 7 outer electrons. So since it has more outer electrons, these outer electrons can feel a greater effective nuclear charge with the nucleus, so that causes it to shrink. So that's what's occurring as you go from left to right. You're increasing the number of outer electrons, you're increasing the effective nuclear charge, you're decreasing the radius. Now as we go down a group, so here we have potassium. So both lithium and potassium have 1 outer electron. The only difference is now potassium has a lot more inner electrons. And since they have more inner electrons, these electrons are shielding the nucleus from this one lone electron in the last energy level. So since it's shielding the nucleus, it's going to push that electron further out because it's not as tightly held, causing the radius to increase. And so that's why we have atomic radius decreases from left to right and increases from top to bottom. Now, with that said, you know, the largest elements are going to be in this section. The smallest elements are going to be in this section. So now we can assign them. So oxygen would be the smallest because it's the furthest in the top right-hand corner. Then, oh, my bad. It wouldn't be magnesium. It would be germanium. Oops, oopsie. So let me just correct these. So next would be germanium. Then it would be iron. And then magnesium. And the largest would be francium. So that would be the ranking of the radii. So next we want to look at, we have this question, which of the following species has the smallest radius? And when we're looking at species that have different, charges, so some are cations, some are anions, we have to look at what are called isoelectronic species. These are species with the same number of electrons. So when you have an isoelectronic species, greater the positive charge is smaller radius, greater negative charge is larger radius. Again, this is only for isoelectronic species, so species with the same number of electrons. So now we have actinide 3+, radon, scandium 3+, sulfide, and yttrium 3+. And so we want to know which of the following would have the smallest radius. So radon and actinide 3+ come from this bottom isoelectronic species. So radon has 86 electrons, and actinide 3+ has 86 electrons. Next we look at scandium 3+. Scandium 3+ has 18 electrons, and sulfide -2 has 18 electrons. And then lastly, yttrium 3+ has 36 electrons. So now, since all these have different numbers of electrons, since we're looking for the smallest radius, we're going to look at the ones that have the smallest number of electrons. If it was the largest radius, we would look at the ones with the larger number of electrons. So since we're looking for the smaller radius or smallest radius, we look at the ones with the smaller number of electrons, and that would be scandium 3+ and sulfide. So these are isoelectronic species. So the one with the greater positive charge would be the one with the smallest radius. And so in this case, scandium 3+ would be the one with the smallest radius. Now, if you were asking yourself the question, which one would be the largest radius? Well, then we would look at the two with the largest number of electrons. And here, radon is the more negative charge. So radon would have the largest radius out of all of these, and scandium 3+ the smallest. Now, with continuing with periodic trends, ionization energy. And ionization energy is the energy needed to remove an electron from a gaseous element. Ionization energy means you have to add that amount of energy to remove an electron. And as we go from left to right, first ionization energy increases. And the reason is because we just mentioned on the previous slides, as you go from left to right, effective nuclear charge increases. the atomic radius decreases. So yeah, as you can imagine, it's going to take more energy to remove one electron from that element or atom, because now the atom is the electron is more tightly held to the nucleus. It's going to take more energy to break it. So as you go from left to right, first ionization energy increases, and as you go to top to bottom, it decreases. And again, it decreases as you go from top to bottom because shielding increases. That outer electron is easier to remove. But with this periodic trend, there are some exceptions to first ionization energy. So when we look at group 2 and group 13, if we look at the electron configuration of group 2, it's going to be general NS2. And we look at group 13, NS2, NP1. Now, since group 2 has a completely filled s orbital, group 13 has a completely filled s orbital, but one electron in the p orbital. Since the p orbital is higher in energy than the s orbital on the same energy level, then it's going to be easier to remove an electron from the p orbital versus a completely filled s orbital. So therefore, group 3 has a lower first ionization energy than group 2 only till about the 4th row. After the 4th row, this exception dissipates. So that's one exception you need to remember. Group 2 is greater than group 3 all the way down to period 4 for first ionization energy. And the other exception is group 5 and 6. So if I draw the electron configuration of those, so for group 5, it's going to be NS2, NP3. And for group 6, NS2, NP4. So now here you see that nitrogen's group has a half-filled p orbital. So every p orbital has one electron, whereas in oxygen, it has 4 p electrons. So that means one of the p orbitals has a set of paired electrons. So since there's one p orbital with a pair of electrons in it, it's easier to remove an electron that's paired up when we're on the same type of orbital than it is to remove an electron that has only one electron, or an orbital that has one electron in it. So therefore, group 6 is going to have a lower ionization energy than group 5. And again, this goes down to period 4. After that, it dissipates. So those are the two exceptions you need to remember for ionization energy. So now we want to determine which one has the lowest first ionization energy. So again, lowest is going to be in this area. Highest would be in this area. So we want to look. Thallium is located over here. We have barium located here. Selenium here. Magnesium. And then silica. So only magnesium and barium are located on the left side, and barium is lower in the group than magnesium. So barium would be the one with the lowest ionization energy. Oh wait, did I just trick? Yeah. And the reason it's not thallium is because after row 4, this exception disappears. So barium would have the lowest first ionization energy. Now with first ionization energies, you can calculate the wavelength of a photon needed to ionize that electron. So here for rubidium, the ionization energy is 403. So again, we're going to be using this equation, E equals hc over lambda. We're going to be needing Avogadro's number. And so first thing we need to do is find the energy per photon. So we're going to divide by Avogadro's number. This gives us the energy per photon. Now notice here that Planck's constant is in joules second, so our energy needs to be in joules. So we convert it to joules. Now we have the energy per photon. So we can plug it into this E equals hc over lambda and calculate lambda. Again, this is in meters. We then need to convert it to nanometers. So we get about 297 nanometers. So this would take a photon of UV wavelength to ionize an electron from a gaseous rubidium atom. And then lastly, we have a kind of a qualitative question for ionization energy. We want to know what main group element in period 6 has the following 8 ionization energies, and it gives us all 8 of them. So period 6 is located down here, and since it's a main group element, we can negate the transition metals and the F block elements. And so here we want to look for is the change between outer valence electrons and the inner core electrons. So what you're going to see is you're going to see a big jump in energy when you go from outer electrons to inner electrons. So what you're going to look for is look to see after which ionization energy you see a big jump in the ionization energy. And so here, if you look at ionization energy 6 is 2100, but ionization energy 7 jumps up to 16,600. So what this tells you is that there are 6 outer electrons for this period 6 element. So if we want to know which main group element it is, we count from cesium. We go 1, 2, 3, 4, 5, 6. So the answer would be polonium. And that would be the one that would have, this could have this set of 8 ionization energies. So you're looking for the big jump to see where you go from outer to inner electrons.